a window. So which one is the right window? This one is the right window. Hello, everybody. Um, so we are gathered here today to talk about decimal types, both in Deephaven and in general in like data and you could say uh, science type system, right? Python has a decimal type, PerK has a decimal type, AVRO has a decimal type. AVRO is one way to encode messages for Kafka. Um, so these types are not, in general, exactly compatible with each other. And the main thing that I would like you guys to remember from this presentation, we're going to talk about, some technical stuff, but I don't expect you to remember like, the whole thing. But the one take home that I would love if you remember after we finish is that it's not trivial to ensure that the data that you have in one system gets to another system when you try to move data around in exactly the same shape because of these like minor incompatibilities that may show up, right? So that's the main motivation. So let me start presenting here. Um, just to confirm, you guys see title screen seeing big decimal types, right?
Yes.
Cool, great. Um, so the motivation first, we are probably all at least slightly familiar with floating point. This is like the float type in Python, which typically matches the double type in other languages like Java, right? Python has a type that is called float, that is really a 64-bit IEEE 754 floating point double precision number. And this thing, the IEEE 754, happens to be a standard that computers implement in terms of how they make calculations with floating point in hardware, and languages implement in terms of how they show the results to you, and they use the hardware to implement operations that you code, right? This being a standard is pretty good because that means that most of the time, for most things that you do, if you do the same calculation in, let's say, Java and Python, you get the same result. Again, not exactly true because there are some caveats to that, but for our intentions today, it's a good approximation, okay? The thing is, these floating point numbers are not exact representation for what we usually think in terms of like base 10, what we use for what we learn in school in terms of like how to operate with fractions. And there are a couple of cases where if you operate in floating point for something that you intend to be a decimal result, you can get surprised about the result that comes back because there is an approximation involved in the computation, right? So I have a little example here. You can find many examples, and there are many good resources in the internet for the pitfalls of floating point. So if some of you are not super familiar with what these problems are, I totally encourage you to take a look there. My little example here is from a mistake that I made at some point in my career. So it's kind of like painful for me. So at some point, I was working in this trading system, and we were supposed to trade when the difference between the bid and the ask in the spread for some name was more than 1 cent, right? So this like very humble looking expression, which is y minus x for two numbers that are floating point being greater than 0.01, was the test that I needed to make. It's like if these two prices are more than 1 cent away, we should do one thing. If not, we should do something else. This thing was not working. We had some examples in production of trades that should have happened that didn't, and I was trying to understand why. And the explanation is that I'm stupid. I did learn about numerical analysis in college. I did have like a full class of the thing, so I was supposed to be aware of this thing, but I guess apparently I forgot. And this doesn't work. And the reason it doesn't work is because none of these numbers are really exact in a floating point representation because we are not guaranteed to have an exact representation in base 2, which is what is used underneath, right? So some numbers in base 2, maybe, for instance, um, maybe what in math happens when you do 1/9 and it has like an infinite 0.9999999 type representation, so it has to be chopped at some point, and those differences mean that when you try to represent in the computer a number like 230.83, right, the number that you get underneath in base 2 in floating point is not exactly the same number that is 230.83 in the real line in math, right? It's a very close number, but it's not exactly that number, right? So when you take the difference of those little differences essentially can mean that things do not fall on the side that you will expect them to fall. So just to ensure that you actually believe me, I'm going to take this thing and I'm going to take this code here and run it in Python. You see, it says it's greater than 0.01, and we know it's not. So it's not right. And why? Well, these may help illustrate why. So you see, the difference here shows what the hell is this, right? I mean, that shouldn't be there. This is there. There's the reason our result is wrong. So anyway, again, what's happening here is this, right? When we type 230.83 in Python, the interpreter needs to turn that into some base 2 floating point approximation, which is not exactly that. So the number inside is not that. Now, you know the funny thing? The funny thing is that when we print it, right? When we print it, it came back as exactly the same thing. So that's kind of like misleading. I mean, it's internally approximating it, but then it prints it back to us. But then we need to think, oh, but you know what? It's printing it back in decimal. So it's taking the base 2 number and doing the same thing again, looking for the best approximation in base 10 to show it to us. So, oh, there are some conversions in between. Anyway, this is one example of potentially many pitfalls in floating point. The one take home here that I would like you to remember is that you should be afraid. Decimal floating point is a hard thing. So when you type expressions, etc., think twice, be afraid, look it up. There are very good resources in the internet. Chip also knows a lot about this thing, obviously more than me. So if at some point you guys feel that maybe that's a good topic to cover, maybe he could give a short run on that. So the decimal type, right? Decimal types are essentially a way to approach the problem of approximations and essentially having an exact representation in base 10. So instead of representing numbers in base 2, what we're going to do is that we're going to represent numbers in base 10. And for doing that, we typically are going to have something simple like we're going to take an integral value, let's say an integer, right? A 32-bit integer that has a certain number of decimal digits. We're not using any fraction there yet, and we're going to say of all those decimal digits that the integer has, we're going to use, let's say, 4 of them for a fraction, and we know that that part, the fraction itself in base 10, is going to be not an approximation but exact. Main need for this, as you could imagine, is financial transactions with money, simple things like your current account and how many cents you have there, because people really don't like getting approximations in their money. So we want like exact results for operations like moving money from one account to another, and we don't want to have to run into the problem of, oh, I'm doing rounding across lots of numbers. How big is the error that I'm introducing because I'm rounding many numbers, maybe all of them rounded in the same direction, and I'm getting like a big offset that is not really there. To avoid those kind of problems, decimal types are the answer. Okay, so Python has a decimal type. There is a library called decimal. The way they work is essentially underneath there is an integral type, as I was describing, with a certain number, with a certain precision. The way Python represents this from the point of view of the API that it gives to you is there is a precision value, which is the total number of digits, okay? So if you have something like 25.3, the precision is 3 because there are 3 digits there, 1 after the period, after the point, the decimal point, even if the fraction is just 1, right? Interesting things about like the Python representation about this library is when you define decimal, right, and you just import these and you use some constructors, this is a class in Python, right, it's an object, and you can pass the constructor and a string, and the string has, you know, quote 3.27 quote, that will give you the decimal representing that number. When you define one of these, that object has its precision. You can define another one with a different precision, and each one of them is going to have its own precision. We don't tend to think about that when we are using things like double float in Java, or the float type in Python, because all of them essentially have the same properties and use the same amount of space, right? Same thing for integer, right? If in Java you have an int, you know, that's 32 bits. If you have a long, you know, that's 64 bits. That's a fixed amount of space that's going to use. These decimal types, each object uses potentially a different amount of space underneath, depending on how many digits you have to represent, right? That creates a little problem, and you need a solution for that problem. And depending on you approach that solution, you have different behavior in different systems. And the problem is, if I take 2 of these decimal objects and I want to multiply them, right? So I have A equals decimal some value, B equals decimal some value, and now I do C equals A times B. I multiply the 2 numbers, right? What is the precision of my result, right? So one potential answer to that is to say, oh, I'm going to do that computation as exactly as I can. So if the result in mathematical terms has 6 fraction digits and 10 integral digits on the left-hand side of the decimal point, then I'm going to use 6 plus 10, 16 digits in total to store the value, right? That's one possible answer. Java Big Decimal actually goes for that. Python does for something different. What Python does is that there is an implicit context where you define for the operations that you do, what precision do you want in the result. That context is like a global variable and affects all the operations that you do, right? So this context, by default, has a pretty big number of digits of precision. So you most of the time don't notice it, but it's important to know that it is there, because there are some operations like division where you're forced to do rounding, right? If you think about it from the point of view of addition and subtraction, if you take 2 numbers represented in base 10 and you add them together, you know that the result is going to be representable in base 10 also. When you do division, because you know there are numbers that have a fractional part that have an infinite representation, right? You know that you can have something like 0.9999999 forever. At some point you need to chop, right? And division across the 4 basic arithmetic operations is the one that can generate unexact results, and where rounding may be forced to happen, right? Even if it's not forced to happen, you can do things in Python for this decimal library where you say, I want all my results to have 4 digits of precision, right? And if you do that and you have something like 0.1234, and you essentially multiply that value by something that means that the result is going to have 6 digits, the result actually is going to be calculated to 6 digits, and then it's going to be rounded to 4 for the final result value that Python gives back to you. Okay? And in the subject of rounding, by the way, there is more than one way to do rounding. Most of the time, we think about the intuitive way to do rounding that we learn in school. I think it's probably just intuitive because we learn to do it that way, so it comes natural. But there's more than one way to do rounding. Actually, there's more like 8 ways to rounding. I have a link there for an article in Wikipedia that explains those types very well. The important thing to know here is that the default round mode in most systems and also in Python is a round mode that is called round half to even, and that doesn't match the intuition, right? The intuition is that if something is 0.1 to before 5, it rounds down, and if it's 0.5 or more, it rounds up, right? That's called round half up, right? Rounds half to even doesn't work that way, and sometimes, depending on the absolute magnitude of the number, it rounds 0.5 up or down, and that has some good mathematical reasons for being that way in terms of trying not to introduce bias when you do rounding of lots of numbers. Let's say you have hundreds of numbers in a column and you are rounding operations in all of them. If the values in your column are like uniformly distributed, then you're not going to have a bias in the result of rounding by using rounding half to even. However, it's not what you probably expect if you're not thinking about this. It's also probably not what a user will expect. So it's a potential source of questions and confusion. Okay, I have a little example there in terms of Python code in the bottom of the slide for how to read a CSV file in Pandas using decimal as the column type for the data frame that Pandas is going to load. Okay, that example combines a couple of things that I haven't mentioned here. I don't want to go into any of the details there, but it's a little bit interesting in the sense that it's not trivial necessarily how to use these types. So you can use it as a reference if you at any time run into something like this. So now from Python, we go to Java, and this is interesting for us because this is what we use, okay? Deephaven has big decimal column type, and when we need to use this type of values, this is the column type that we should be using. And we essentially use the big decimal implementation in the Java standard library. I have the link to the Java out there. Things that are different, slightly different from the Python library is that the big decimal representation uses separate explicit precision for the total number of digits. So it's the same concept as in Python, but also it uses an explicit scale, which is the number of fractional digits. So if you have something like precision 6 scale 2, that means that you're going to have 4 digits to the left of the decimal point and 2 digits to the right. Okay, and when you build one of these values, when you use the constructor to create one, the precision and the scale are either implied or you tell in the arguments explicitly what do you want. Okay, and as you can imagine, right, the scale is going to be used in an internal representation as the exponent in an implicit multiplicative factor of 10 to the power of minus that scale. So, if its scale is 2, 10 to the minus 2, that gives you the 2 decimal places. An interesting thing here is that it can also be used in the other direction. The scale can actually be negative, and in that case, you can have numbers like 300 represented with just one digit because the 2 zeros for the 100 parts is part of the scale. That's not very frequently used, but it's an interesting thing to be aware of, especially if at some point, for some reason, you make a mistake and pass a negative scale and you didn't intend to, and the numbers begin looking funny. Not that has happened to me ever. There is no implicit global context here. So unlike Python, where in Python there is a global context variable that affects how operations in decimal that you do round, in Java, each operation in the argument, right? If you say big decimal dot multiply and you give another big decimal as parameter to do a multiplication, that operation can take doesn't have to, but can take an object of type math context, which is similar to the Python context. It also specifies what is the precision and scale that you desire in your result, and what type of rounding do you want to get there if the result cannot be represented there exactly. Okay. Um, Important things to know is that if you do not provide a context, the operation defaults to try to be exact. And as we were discussing before, that's going to be probably fine for addition, subtraction, and multiplication, but division is going to create a problem for us because there's no guarantee that any two big decimal numbers, when you divide one by the other, you're going to get an exact result. Or a result that can be represented in a finite number of digits. So beware, division with non-context can throw. So in general, you do not want to be doing this. You want to be passing a context to a call to a.divide b, because otherwise you can get an exception. Okay.
So are you saying that by default 1 divided by 9 throws an exception?
Yes.
Okay. Interesting.
Yeah. So from the point of view of Deephaven table operations, okay, we recently implemented operation overloading in the query language. So it used to be the case that if you wanted to multiply two big decimals in a column expression, you will have to say column B equals column A dot multiply dot column C, right? Now you can always continue to say that, but now you can say A star B and it works, which is great. Now, from the point of view of division, right, to get the division operation overload to work, and given what I just said, we have to have an implicit context. So in Deephaven, we have one, and it does what I wrote there by default, and it can be changed to do something else if you want something else. But sadly, at this point, if you want to change this context, unlike in Python, where you can change it on the fly and continue working in the same Python interpreter process instance, in Deephaven, this is something that you can set on a startup, eat a property. If you want to change it and have different behavior, you need to restart the server. Where are context applied in general? And some of these happened before that change for supporting operations that I described before. It also happens in the age grouping operations, including in Deephaven's grouping operations, including big decimal columns. You imagine that if you do a grouping and you do an average, right, that implies a division, so it runs in the same issue. It also uses rounding mode half-out by default. Which and the reason for that is that it's less confusing for users. It's not the most mathematically sound decision, but is the this is the way we get less questions decision. Okay, so that is Python and that is Deephaven. Now for other systems and ways to storage data that you may want to get in or out of Deephaven, PerK, AVRO, etc. Right? In PerK, decimal is a logical type annotation that includes two integer parameters, precision and scale. So it's similar to what we saw before for big decimal there, right? The part where this is different is that decimal in PerK is not a single type, it's a family of types. And when I say a family of types, what I mean is that the type itself is the combination of decimal with a particular precision and scale. And what that means is that when you choose a precision and scale, it applies to all the values in the column, right? Unlike in Python, unlike in Java, big decimal, and in Deephaven, every individual decimal value in a column does not have its own precision and scale. There is a single precision and scale that is supposed to apply to the whole column, okay? That saves us some trouble because it gives us an implicit target. There is no need for a context when we do operations with two values in this column. right? It's, I mean, what precision I'm going to use for the result, what scale I'm going to use for the result. Well, it's obvious you want to use the precision and the scale for wherever you're planning to store this. So for the resulting column, you take the precision and scale from there and use that, right? When we say logical type, many of these systems, AVRO, PerK, AVRO, use the concept of logical type versus physical type. Physical type is the way to store actually bits underneath, and logical type is the way to understand those bits in a different way than the default. So to give you a very simple example, right? We're used to think about timestamp being a long and representing a certain number of milliseconds. The logical type there is the long, the 64-bit integral signed value, right? That's the physical type. The logical type is I want you to understand those bits there as a certain number of milliseconds or nanoseconds or whatever from a particular, arbitrary starting point in the past, right? Decimal here is an annotation that you give on top of a couple of decimal of different possibilities for physical types. That essentially gives us a flexibility from the point of view of how much storage we're using underneath, right? Because we know if we use a 4-byte int, like an int32, that's going to use less space than using an 8-byte int64, which is a long in Java parlance, right? In the actual storage underneath. And maybe there are enough decimal digits in there, right? So that we don't need int64 and we can live with int32. But, libraries that implement these systems abstract these from us. We just get the actual decimal when we read it back. So this is just from curiosity's sake, or if you happen to navigate in the code and see this. Or also it's useful if you need to read the spec to understand why some particular behavior is happening, right? It's interesting context for being aware for reading the spec. One implication is that precision and scale should be compatible with the underlying physical type. So for instance, right, you know that in practice, the biggest value that you can store in a 4-byte integer is around 2 billion, right? 2 billion means that the total number of digits that you're going to be able to store there is not any number. You're not going to be able to store 20 digits in something that cannot be bigger than 2 billion, right? So precision and scale need to match the underlying physical type as to not be bigger than the maximum that can be stored. That's it. Okay, that was PerK. AVRO. AVRO is a specification for schemas that is used in multiple places. One interesting place for us and where Deephaven uses it is for Kafka encoding of key or value fields, right? It's a binary representation, which really makes the Kafka messages smaller because it's more compact than a representation like JSON, which is, strings. It also includes 2 integer parameters, precision and scale. Again, not a single type, a family that applies to the whole column. The logical type annotates one of 2 possible AVRO types that are either bytes or fixed. Bytes in AVRO is an arbitrary length string of bytes. So it can be as big as you want. Each value, other than the string itself, says how many bytes it has. So it's kind of like an array of bytes. And fixed is you say in advance, every value in this column has exactly 6 bytes, for instance, right? Same thing, they should be compatible, precision and scale, with whatever the underlying physical type is. Okay, so AVRO and PerK, pretty similar. AVRO, also like AVRO and PerK, precision and scale. One difference, though, by the way, is that thing that Java was able to do in big decimal, making the scale negative so that you can present hundreds or thousands or something like that. These guys do not support it, neither of them, okay? That's a Java specific thing. The underlying concrete type here, the physical type, can be just one of 2 things. The choice that they made in AVRO is either 128 bits or 256 bits. That's it. You don't have more choices than that. That's a lot of digits. So typically for simple-minded things like, database SQL type columns that represent the price in an e-commerce website, you are going to be totally fine. Barrage. So Barrage, our Barrage, Deephaven's Barrage, is a special case of AVRO. We do not have full support for every AVRO type yet, though. Barrage is a work in progress, right? In particular, Barrage does not support today decimal as an AVRO logical type. So when you read this, you're like, huh, but we know that big decimal works in Deephaven in the web client, so what gives? Well, we have a hack. We have a way for the server and the web client to understand each other when the server is sending big decimal Java types. It does not encode them in the AVRO canonical representation for decimal. And there is a good reason for that. If you think about it, right, this difference where each individual value can have its own precision and scale versus the whole column having to have the same precision and scale means that we are in trouble here, right? If we're sending ticking data, how do we know in advance what a perfect representation for anything that we may see in the future is in terms of precision and scale? The answer is we don't, we can't. We could do some kind of approximation, hope for the best, etc. Maybe we do something like that in the future. It's not a real problem. We're not doing it now. Yeah, so that's it. Ancillary, interesting when you're moving data from SQL databases like MySQL or Postgres or, God forbid, Oracle. SQL has a decimal or numeric type. It has had like since forever. This is a pretty old spec. Actually, the numeric type is very, very old, and relational database did not used to have historically like anything else from the point of view of numerical type, right? If you ask in the mid 80s in like 1985, oh, I would like to store a 4-byte integer in my database, how to do that? The answer would be what? They added all that at some point later because programming languages, you typically need to interface code with databases and store things, and it was necessary. But numeric is very old and it has a precision and scale, right? The sad part of the story, though, is that the SQL spec talks about precision and scale and column representation, but it says nothing about rounding and how to compute results. So that's going to be an implementation detail of the particular database system that you're using. So if you face that, consult the friendly database implementation manual. Summary. This is a little bit of a zoo. There are a lot of differences between different systems. Things to remember and take home, okay? Python decimal calculates with an implicit context. We saw that. There is a caveat. That implicit context is not used for constructors, okay? So you can set an implicit context where you say, I want to use two digits of precision for my computations. And then you create a big decimal with an argument of, quote, 3.456, close quote. That actually has 4. And that's fine because the context is not used for constructors. It's just used for operations involving the decimal object. So if you multiply that by some other decimal, then in the result, you're going to get the context applied and not rounding, but not in the constructor. Java decimal, as we said, has no context. Operations that are not given a context do exact by default. As we saw, division control, beware. Big decimal division operator, and only division in column expressions, has a hard-coded context that you can change by setting a property when the system starts. PerK, AVRO, and SQL define a family of types, unlike Python, Java, and by extension Deephaven. This system, PerK, AVRO, and SQL, define a decimal type with a precision and scale, and that combination creates a type that essentially applies to a whole column in a table. Okay, This allows them to escape the need for defining some kind of implicit context in some way or making that context explicit. And it means that any results calculated to be stored in a column automatically know what precision and scale to apply because it's a property of the column itself. Okay. One interesting thing to think about is that PerK, AVRO, and ARROW, they are essentially exchange data formats, right? They do not define results of operations because they only define data at rest. So you don't need to think about how I'm going to multiply two ARROW values in an ARROW column to generate an ARROW column for the result. That's not an ARROW problem. That is some system using ARROW problem. ARROW only specifies how it's going to be reading and writing data to you and from you. Same thing for PerK, same thing for AVRO. Okay? So they never, if you look at the specs of the thing, they never talk about rounding, they never talk about precision of results because they don't need to. Okay? SQL needs to because you can write a SQL statement that says this column is the result of adding these other two columns. But the standard doesn't say anything, it's silent about it. This is interesting to remember because it's kind of counterintuitive. So I'm making it explicit here again. ARROW limits the underlying representation. You have two choices, and that's it, and they're hard-coded. So when you specify precision and scale, it's more of a matter of how I'm presenting the results to you more than what the underlying representation is, because underlying representation is pretty restricted, okay? It is still pretty big, so most of the time you don't see this, but warning, caveat there. This is a little table of the current support for reading and writing and conversions of decimal types from and to Deephaven tables. The no there for ARROW has to be taken with a grain of salt because we support moving big decimal itself, right, between the web client UI and the Deephaven server, right? The asterisk there is because in Kafka AVRO 2 big decimal, like we said before, right? If we have a context where we are taking data from something that generates values that have precision and scale for every value, and we're moving data from that to something where the whole column has the same value, there has to be some conversion in there, okay? So when we exhaust data from Deephaven to a system where there is a column with a defined precision and scale, we have two options. Either the system itself does something where it finds a best precision and scale. We do this for PerK. If you take data from a table in Deephaven with big decimal and you write that to PerK, the big decimal operation to write PerK there is going to look at all the values in the column and is going to decide on, okay, what is a precision and scale that I can use in PerK so that I don't lose data in the process, and doing that decides on what type to use for PerK. In the AVRO case, we need the user to actually specify this, and it's not like this. This is an example of producing data to Kafka from Deephaven, and you see there in green, this is new syntax, it was added recently. In the spec for the value for AVRO, we are passing an additional argument that is called column properties. And what you do is that you say column name dot precision, you give a number, column name dot scale, you give a number, and that way you're telling Deephaven when you write to AVRO, you need to apply this precision and this scale. The reason we need to do this is because when we produce, unlike when we write to PerK, right? When we produce to Kafka, we may be producing from a taken table, right? In the PerK case, you always know exactly what you're going to write when you write it. There's no future, right? It's like, take all this data, write it now, right? When it's like that, we can take a look at all the values that are there now and pick a precision and scales for you. When you have a ticking table, right, there's no telling what future decimal values, big decimal in the case of Deephaven, are going to show up 3 seconds from now. So we cannot do that. We need the user to tell us, do this. So that's it. And I'm totally over time. Apologies for that. If you guys are not totally bored by now, and we have more time, and you want to entertain it, I totally understand if people have to leave. But I'm happy to stay here and answer any questions that you guys may have.
Right. Any questions?
Yeah, I got a question.
Yeah.
Is there any known issues with performance on using, these big decimal classes, such as like, arithmetic or memory usage or anything like that? Like anything we should be aware of based on, or as a comparison to like, native integers and floats?
Yeah, that's an excellent question. This what I'm going to say is both true for Python and Java, and from Java by extension to Deephaven. Okay. Imagine this. Okay. Imagine we're storing an integer column in Deephaven, right? This is mostly going to look in memory like, it's not going to be exactly, but it's going to look like an array, right? And how do you expect an array of integers, 32-bit integral type, right? 4 bytes, to look in memory? Well, it's going to be 4 bytes, another contiguous 4 bytes, another contiguous 4 bytes, another contiguous 4 bytes, right? That's a pretty compact representation, very packed, very not wasting any space, right? In both Python and Java, in particular Java for big decimal, when you have an object in a column, right? And big decimal columns are object columns. It's a Python object there. It's not a primitive, right? What you have in the column is not the value itself, it's a pointer. So that's a first source of inefficiency from a memory perspective, right? You are not storing the thing there, you're storing a reference to the thing. So in storing a reference to the thing, you already made this inefficient in either 4 bytes, if your Java virtual machine is using less than 30 gigabytes of heap, or maybe an 8, if you actually need 64 bits to represent a reference in memory, if you're running like with huge memory, right? That's a detail of how virtual machines work. But anyway, you're wasting the reference storage there because the actual object is somewhere else in memory, right? Now, an object itself in Java, it's also a pretty big thing, because an object has 12 bytes of a prefix specifying some things about type and other things, and then it has the actual payload for the object, right? In Java. And God forbid, if you have the payload of the object, and when I say the payload of the object, what I mean is you have, class in Java, right? And the class has some data members. So let's say your big decimal class definition has one data member inside that is called big integer to represent the actual precision digits, right? So really your internal representation is, if you have a scale of 4, you store a big integer, and you know that the last 4 digits are the scale, the fractional part, right? That's how you represent it internally. Well, then your big decimal object in memory is going to have another slot with a pointer, a reference to another object. So this jumping around in memory is totally not friendly for the CPU cache. So that is not good. The memory used for this is also not great, because there's a huge overhead for the actual data that you're storing. So yeah, not happy land. Very, very, I'm not going to say bad, because good or bad is going to depend on your actual use case, right? But I'm going to say a lot less efficient than a compact representation like what you would expect for, double or int. Yeah.
So, Cristian, related to that, can you talk a little bit about where people actually use this?
I encountered this when I was doing the Divisium demo conversion from the materialized script in SQL. So I ran into this first in a practical use case example, right? Because I had run into it when I was doing implementation of AVRO, implementation of PerK, because it's one of the types mentioned in the spec, right? So we had to think, oh, how to do this. But from a practical perspective, I ran it first in the SQL for materializing their demo, because in their e-commerce website demo, they have prices, right? So it's like, the demo, it's about some gadgets that you can buy in a website, and each gadget is an item that has a name, and there's a price that you're selling that at, right? Traditionally, canonically, and rightfully, if you want, the type for a price, right, is decimal. It's not float. It's not double, right? And that makes sense. And the reason that makes sense is because otherwise you can be Christian and make mistakes and like, you know, do operations on those numbers that are going to give you results that your users are going to look at the shorts and they're going to say, what? So yeah, it's the right thing to do, to use decimal types for things that look like prices. And you can kind of extend that to financial transactions in general. Maybe you can kind of extend that to trading, etc. In trading systems, you know, for the one of us that have worked in, like, you know, high frequency trading systems. High frequency trading systems do a lot of things having to do with performance and trying to be low latency. So those pitfalls that we talked about from the question from Jacob prevent us from using those things. But we do other things like use integers and remember what the scale is to avoid using floating point, right? You should not be using floating points for things that have to do with prices. And in general, they show up a lot in the SQL world and in the relational world, and some in the data world when they represent data coming from financial transactions or financial applications.
Right. Any more questions for Cristian? All right. Thanks, Cristian.
See you guys.